Okay, see. So yesterday we have learned orthogonal complements and the theorem, which is if M is a proper closed linear subspace of a Hilbert space H, then there is a non-zero vector Z0 in H such that Z0 is perpendicular to M. So we have seen this proof. Okay. We see the theorem. See definition first. Two non-empty subsets S1 and S2 of a Hilbert space are said to be orthogonal if X is orthogonal to Y for all X in S1 and Y in S2. That means what? The two sets, we have given the two sets S1 and S2, and these two sets are, earlier we have seen two vectors are orthogonal, then a vector is orthogonal to the space, that is to the set. Now we have to see the when two vectors are said to be orthogonal. Okay. So if we have a vector, first vector is X and second vector is Y, then that X belongs to space S1 and Y belongs to space S2. This condition should satisfy for all the vectors belonging to these spaces. Okay, that means for all X belongs to S1 and for all Y belongs to S2, that two vectors should be perpendicular or should be orthogonal to each other. Then we say that these two spaces S1 and S2 are orthogonal. Okay. So this is the condition, that is S1 is orthogonal to S2 if and only if X is perpendicular to Y for all X belongs to S1 and Y belongs to S2. Now see, if the theorem, if M and N are closed linear subspaces of a Hilbert space H, we have given two closed linear subspaces of a Hilbert space H, okay, such that two spaces that M is orthogonal to N, then the linear subspace M plus N is closed. We have to prove that subspace M plus N is closed. Okay. See, given that what is given, M and N are subsets of H. That means they are linear subspaces of a closed linear subspaces of H. Okay. And we have to prove that. And also given M is orthogonal to N. Then we have to prove that M plus N is a closed linear subspace. That means any limit point of that space M plus N should lies in that space. Okay, we have to prove that any if we consider any sequence from that set or that space M plus N, then that should be that converges in that same space. Okay. See, so we have to show that M plus N is a closed linear subspace of H. Let Z be a limit point of M plus N. Z is a limit point. Okay, that means there should be a sequence which converges to Z, right? So it is sufficient to show that Z is in M plus N. What is the definition of closed set? Definition of closed set is what? Its limit point should lie in that set. Okay, then we say that particular set is closed set. Okay, so here we have considered Z is the limit point of M plus N, and it is sufficient to show that Z lies in that M plus N. Okay, as Z is a limit point, then there must be a sequence. Therefore, there is a sequence. Madam. Okay, so let Z be a limit point of that M plus N, then it is sufficient to show that Z is in M plus N. Okay, as Z is a limit point, so there is a sequence that is Zn which is in M plus N, which converges to Z. Okay, that is Zn tends to Z. So what we have given, M is perpendicular to N. That means M and N are disjoint, because when two vectors, when we said there is only zero vector between these two sets, M and N. Okay, that means what? We said that two spaces are disjoint. Okay, and because every vector from M is perpendicular to N. right? And that is why there is no vector exists which is perpendicular to itself, and therefore there is no any common vector except 0 between these two spaces, and that is why we said that those two spaces are disjoint. Okay, therefore each Zn can be written uniquely as these two spaces are disjoint, then every sequence in M plus N can be written uniquely in the form of this form: Zn is equals to xn plus yn. Okay, where xn belongs to M and yn belongs to N. Now consider norm of Zm minus Zn. So it is written as norm of Zn minus Zn is equals to norm of xm plus ym, because every element from M plus N is written in this way. Okay, so it is xm plus ym minus Zn. Value of Zn is xn plus yn. Okay, so now this is equal to xm plus ym minus xn minus y. So this is same as norm of xm minus xn. We have taken together the terms of xx and again the terms of y. Okay, so it is norm of xm minus xn plus norm of ym minus yn. Okay, so by Pythagorean theorem, see, we use here the Pythagoras theorem. By Pythagorean theorem, we know that norm of x minus y bracket square is equals to norm of x square plus norm of y square. So it is written as norm of Zm minus Zn square is same as norm of xm minus xn square. This is first term of this norm, and this is second term, plus norm of ym minus yn square. Okay. Same by Pythagorean theorem, we know that norm of x minus y square is same as this. So this is also okay. Therefore, xn and yn are Cauchy sequences in M and N. Why? Because M and N are closed linear spaces, and if we have a closed space, then every that limit point of that space should lies in that space. Okay, so a sequence should converges to the same space. Okay, therefore xn and yn are Cauchy sequences and M and N, and therefore since M and N are closed, that implies these spaces are complete. That means every Cauchy sequence belongs to this space should converge in same space. That means xn and yn converges to M and N respectively, and therefore there exists a point x belongs to M and y belongs to N such that xn tends to x and yn tends to y. Okay, as Zn is a sequence in M plus N, Zn is a sequence in M plus N, and therefore x plus y belongs to M plus 1, M plus N. As Z is a limit point of that sequence, that means Z is equals to limit of Zn. So which is equals to limit value of Zn, xn plus yn. So it is separate, by separating limit we'll get limit xn plus limit yn, and that is limit of xn is x and limit of yn is y. That is equals to Z is equals to x plus y, and that x belongs to M and y belongs to M implies that x plus y belongs to M plus N. This implies that Z belongs to M plus N, and what we have taken, Z is a limit point from, we have taken Z is from M plus N. Okay, that means M plus N is a closed space. Okay, and we have shown that Z is in M plus N. That means that M plus N is a closed space. Okay, and this completes your proof. Now see the theorem. M is a closed linear subspace of the Hilbert space H. Then we have to show that then H is equals to M direct sum with M perpendicular or orthogonal complement of M. See what is given. Given that M is a closed linear subspace of H, okay, we have to show that M is equals to H is equals to M plus M perpendicular. Okay, as M and M perpendicular are orthogonal, they are orthogonal to each other and also closed linear subspaces of H. Therefore, by previous theorem, what will have M plus M perpendicular is a linear subspace, right? Okay, so M plus M perpendicular is a closed linear subspace. Why? Because we know that if we have a Hilbert space and if we have two closed linear subspaces of that space, Hilbert space H, then their addition is also closed linear subspace. That means here M and M perpendicular or orthogonal complement of M both are closed sets, subspaces of particular Hilbert space, and therefore their addition M plus orthogonal complement of M is also closed linear subspace of that particular Hilbert space. Okay. Now, see, we prove that M plus M perpendicular is equals to H. Here, we have to show this. Okay. If M plus M perpendicular, suppose we prove this theorem by contradiction, that is, suppose if M plus M perpendicular is not equals to H, then what will have? Then there should be a vector which is non-zero such that that vector is perpendicular to that whole space, that is Z0 is perpendicular to M plus M perpendicular. Okay, that means Z0 belongs to M perpendicular. We have taken its perpendicular, that is perpendicular of that whole space. Okay, that is Z0 belongs to M perpendicular intersection M double orthogonal double complement of that M. Okay, but which is not possible. How? That means this M double perpendicular what, which is a subset of your M. Okay, by previous remark, which is subset of M, and there we have seen earlier there should not be a vector which is non-zero and that vector lies in both M as well as M perpendicular. There is only a vector which is zero vector which lies in both M and M perpendicular. Okay, so this is not possible, and therefore our assumption that M plus M perpendicular is not equals to H, which is wrong, and this implies H is equals to M plus M perpendicular. This implies what? H is equals to M plus M direct sum with M perpendicular, and this is your proof. Okay. Now see, orthonormal sets. When we said that two sets are orthonormal. Okay. See, an orthonormal sets in a Hilbert space H is a non-empty subsets of H. See, orthonormal set is what? An orthonormal set in particular Hilbert space H is a non-empty subset of H which consists of mutually orthogonal unit vector. That means that set consists of two vectors which are orthogonal, mutually orthogonal, as well as they should be a unit vector. These two conditions, if any space satisfy these two conditions, then that space is said to be orthonormal space or orthonormal set. Okay, that is C. Orthonormal set is a non-empty subset EI, which is a collection of EI of H with the following properties. That is, first property is I is not equals to J. For all I not equals to J, EI should be perpendicular to EJ. And second, norm of each vector EI is 1. Okay. If now see the property, if H contains only the zero vector, if H contains only the zero vectors, then it has no orthonormal sets. Okay. If a space contains only zero vector, then it has no orthonormal set. Okay, keep in mind. Okay. That means there should not exist, if H is a zero vector, if H contains only zero vector, then there should not exist another vector. And if we take that is perpendicular to that zero vector except zero, and that second condition also not satisfied by this zero, that is norm of AI is 1, that norm of 0 is again 0. Okay, so this is your property. If H contains a non-zero vector X, now see here it is non-zero vector. Okay, so important condition, if H contains a non-zero vector X, and if we normalize X by considering, we have to normalize X, that normalize means we have to make it unit vector. Okay, now see, we normalize X by considering E is equals to X divided by norm of X. This should give you a unit vector. Okay, this will give you the unit vector. Okay, then the single element set E, singleton set E is an orthonormal set. Okay, in general, if Xi is a non-empty set of mutually orthogonal non-zero vectors in H, and if The xi's are normalized by replacing each of them by ei is equals to xi divided by norm of xi. Then the resulting set ei is an orthonormal set. Okay, for example, see the example, the subset E1, E2, En of L2n, where ei is equals to 0, 1, and it has one value at ith place. Okay, and other entries are 0. Ei consists of 1 at ith place, and other entry of that vector is 0, and it is n double, n times is a orthonormal set. Why? Because if you consider the first property, that is this ai perpendicular to ej, that means their inner product is 0, then it is obviously 0 for all I not equals to j. And if you consider norm of any vector ei, then it must be 1. Okay. And second example is if en is the sequence with 1 in the nth place and zeros elsewhere. This is a sequence en which having 1 at nth entry is 1 and remaining all entries are 0, and this is infinite sequence. Okay, then e1, e2, en and so on is an orthonormal set in N. Okay, so okay, we will stop here.